Okay, now we're going to discuss about some concept regarding the CFD itself and the modeling. Of course, based on our discussion before, based on Navier-Stokes equation and the boundary layer definitions and etc., yet it is a little bit to be complicated with respect of in case of separation happening, vortices and vortex and etc., which is will be like here, which is will be a way difficult. Yes, it can be simulated, but it will be little be difficult. So there is some correlation defining especially the boundary layer condition, especially the boundary layer condition, to try to lower the computation the computer power or the computation power, the computing power to reach to a certain solution. Of course, we understand if it is laminar, it is a laminar, but if it is a turbulent model, so there is some correlations and some way of defining that change, which is mean. For example, there is a model named K epsilon model, and there is another model which is named K omega model. There is another one which is DNS, and there is way other than only those, but this is the most famous, this two, and this one which is the most accurate. Okay, what does it mean? K epsilon model, it is the turbulence, kinetic energy of the turbulence, which is if you have a turbulence due to separation and etc., so there is a kinetic energy for that vortex, okay, or for that turbulence, and epsilon is the dissipation of that kinetic energy in time. So we assume that, for example, we have a kinetic energy of 10 joule in one vortex here. When it is become, we know it's going to be dissipated in 2 seconds. So the entire energy be 2 seconds. So this is the epsilon. Okay. How it is being solved? Under K epsilon model, we have 3 models, which is the standard model, the renormalization model, which is RNG, and there is a realizable realizable method for the KEPS, all based on KEPS, all based on the same concept. I have kinetic, I have dissipation of the kinetic per time. Okay, so the standard method is, of course, it will be less computing power. It is accepted accurate, which is means not meaning like it is giving wrong numbers. So it is accepted accurate. Yet you need to understand what is application and its limitation. Its application, if you have pipe flow, if you have heat exchanger, which is you are concentrating about the heat transfer, you have a heat transfer application, or you have a simple wind system for low building, or like it's not super high rise, which is a lot of vortices happen. Simple one, yes, it can be accepted, and for heat transfer and heat exchangers is accepted. Okay. Its advantage, of course, it is less computing power, which is mean fast, farewell good, which is accurate, accepted accurate, but it is very weak in separation. If you have a separation and you need to study the separation, for example, if you have an aerofoil or the model what you are doing, its question is what is the separation? Like, for example, you have an aerofoil, or you have like what we discussed here, the stall effect. So if you're going to ask yourself about this stall effect, or we write it, however. So if you are asking yourself these questions, so no, it is not. Okay, but if you don't care what is happening, if there is separation, what is, you don't care about the forces, you just need to check what is the heat transfer coefficient, or some basic forces. Yeah, it's okay. Okay, how it is one? It is run based on defining the viscosity for the turbulence. It is rho C mu. C mu is a solid number or a number, which is K. K, it is here, kinetic, and the distribution. Based on defining C mu, it is almost 0.09. So the software will check what is the kinetic energy generated here divided by the time. He will get the viscosity of that turbulence. Okay. Okay. Renormalization method or model. It is a little bit higher computing than this one, and it can take high vortices or high vortex flow. It can take it. Example, fluid machinery. For example, if you have fluid machinery, there is a separation happening in fluid machinery. Or complex wind system. Complex wind complex, which is mean you have a super high-rise building, which is there is a lot of vortex. Yes, you need it. It is same as a standard flow as this one, but it take in account another correction factor, which is it is still the same definition, but C mu is different, and even it is having a self correction in the model itself, but it is using the same fundamental, but in addition there's another step inside. Okay, however, it is in the logarithm of the computer. Okay, there is something which is realizable method, which is k epsilon. Also, it is the newest. It is more and more higher computing power. Now yet C mu, it is a function of a node and as, which is, and also function of the velocity and the time. Okay, it is way complicated, but it will generate more accurate CU, which is based, will be its application. You have an airfoil. You need to triple check what is happening on the airfoil for stall, and it is, it's your study is not the forces, it's your study, is there the separation or no, or in a high pressure, if you have a high pressure gradient, remember high pressure gradient, which is giving a high possibility of separation. Or if you are using a smoke, why if your application is using a smoke, because if you have a multi-phase, there is a lot of vortices happening due to the multi-phase. So when smoke is a multi-phase, by the way. So for any species, which is mean reaction and very reaction, or a multi-phase or a separation, you need to use the more accurate one to generate the entire vortices of all uh, what is happening. It is very good in dynamic viscosity, rotating, uh, stationary, adjacent zones fluid. This one, which is mean if you have two zones and one zone is rotating, another zone is not rotating, no, it cannot do it. For this case, it cannot do it. Okay. K omega model. K omega model, it is mainly to check a certain. This is for airfoil. Okay, now this one, no, it is a certain area of the airfoil, which is like, for example, at the tip itself. So you are taking care a small part, which is you need to know what is happening on that area. It is using very high computing power. You use a standard method in case of low Reynolds number. Use SST model in case of high Reynolds number. Its application, which is you are very near to the wall itself. Okay, so you are checking what will happen to the wall, to the very near the wall. Okay, the DNS method, it is more accurate, yet it is very high computing power, which is can cover all, but it will take way longer time. So okay, okay. So in general, what is happening? In general, because you have, for example, flow in the pipe, so flow velocity is a change, and you need to remember to make an averaging in the Reynolds number like this. So because the change in the kinetic energies in the vortices here based on the epsilon, which is here, this is what we are doing, is averaging the Reynolds number. Otherwise, you will have very fuzzy flow. So this model is making averaging of the Reynolds number by checking what is the kinetic energy for the turbulence and what is changing the viscosity based on that. This to reduce computing power. Okay. Now there is something else we need to understand is the current number. Current number, it is a dimensionless number for simulation, which is defining the stability of the solver, which is mean, imagine that is you have a mesh and you know that is this piece of mesh going to move from here to here in a certain dt. So velocity multiplied by dt divided by the characteristic length of h. So by default, if h if c is way high, that is mean either h is big or the velocity is very high. So if assuming that is h is big and the velocity is not high, that is mean this mesh has been moved like this, but still part from this mesh between the other two. You understand me? So the approximation get not good, or the velocity is very high, which is mean this mesh will jump way over other meshes, so it will be very complicated to solve. That is why we need to keep the current number as low as possible. Usually it should not be bigger than 2.5. How we're going to know it? Approximation, we need to say, we know that is our application velocity is between, for example, 2 meter per second till 4 meter per second, let's say 4. So our mesh is like this. So, and we know that is this mesh can move uh, this 4 meter per second. This one is the simulation delta t as a transient mode. We are going to say, okay, make the simulation for the transient mode each 0.1 second. So 0.1 second multiplies this one divided by h, the mesh size, will get the current number. Okay. Normally it should be less than 2, maximum 2.5, but if we find that it's diverging, you need to keep it less than 1. If it is still diverging, so you need to keep it less than 0.1 or 0.5 at the startup till everything is settled. We're going to understand what I am saying, but it is very important points. A lot of CFD analyzer get hard time to understand how the program is thinking and what is the transient mode, how to manipulate with what we are getting. Okay. Now the pressure base and density base solvers. In the CFD, there is an algorithm which is either based on pressure base or density base solver. What is this? See, in the CFD, normally, if it is based on pressure base, what is happening? The CFD program going to assume what is the pressure, assuming. Then it will get velocities from momentum equation. Then a correction factor, going to use it with some correlations and some equations to make, and it is like an iteration, like like what we done in looping analysis, if you remember. That's why I put it. You see what I done here in looping analysis, which is, it's not CFD, but it is the same concept, same phenomena, which is they are after assuming the pressure and getting the correction factor of the pressure with some of the equation. Okay, then it's correcting the pressure, then from the above, so then from the new pressure applied, getting the density. If the density is changed, then applying the new pressure, new velocities, and make some iteration. So each time step, maybe we'll have 10 iterations, which means pressure, velocity, density, pressure, velocity, density, pressure, velocity, density, correction, pressure, velocity. Maybe 10 iteration, 5 iteration, 20 iteration, which is you are defining per each time step how many iteration you have: 10, 20, 100 iteration. More iteration, more accurate solving. And if you less iteration, less accurate solving, which is giving you wrong numbers, which is pushing the entire solver to be diverge, which is there is no any solution going to happen. Okay. What will okay? Why we need a density base? We understand the pressure base how it is running. Okay, density base, a pressure base if it is a Mach number less than zero point 0.3, which is we know an approximation it is incompressible. Yet the density is going to be changed due to a lot of parameters, but it will never change due to the flow itself. So density can be changed if you force all the air to push in a wall, so density a little bit, the pressure will increase, density will a little bit increase. But in case of Mach number bigger than 0.3, density is a function of the flow itself, diverging, converging, etc. So if it is the flow application which you are dealing with over than 0.3, like you are dealing with machinery, you're dealing with rockets, etc. Yes, the above is the same, but from continuity, after you get this one, for momentum, you need to apply continuity. From continuity, you will get the rho, because now the rho will be inside the continuity equation, not as a constant. So from rho, you will apply B equal RT, you will get B. Then from B, you will start make the correction factor, then repeat again from start from the momentum. So it is an additional step. It will take too much time, and it is for compressible flows. Okay, okay, okay. Now there is something which we need to understand. Now we understand what is the turbulence model we need to select. Now we understand what is the current number for meshing. We understand what is the philosophy of fluid, which is it pressure based or density based. Then the solver itself. How is the solver going to solve the full body of the unit? The solver, which is based on pressure velocity coupling algorithm. Pressure velocity coupling algorithm, it is a steady state, which is symbolic or piezo, and also we have another one, assembly and Bembly. Okay, it is not names, it is expressions. Um, each letter is presenting, for example, pressure independent. I don't remember what is it, but at the end, this is an algorithm, which is mean how the solver going to think. Okay, symbolic. It is application is for steady state. It is fast, uh, but which is it will be fast in the steady state. However, it will take, for example, one portion of time, but Bezo will take three portions of time. So it is fast. Okay. And it using a pressure relaxation factor, which is almost one or less. Okay, which is maybe 0.7. Of course, you can use this one. The pressure relaxation factor. It is a factor which is it is damping the shooting in the pressure. If, for example, the pressures you find it is unstable, which is mean not diverging. It is unstable, which is mean you start like this and like this and like this like this. So use it in case of it's not stable. Lower it. Okay. Okay. The pressure relaxation factor. It is uh, from the pressure and from the momentum, because the pressure relaxation factor, it is a factor which is going to affect pressure relaxation factor due to pressure change and due to momentum change. Okay, usually pressure change it is zero point 0.3 and 0.7, it will be more than sufficient. Okay, this one is can use for piezo, is its application, not steady state, it is for transient. Or if you have a scalar, which is mean two flows with, we'll discuss about the scalar after, which is mean you have two flows, and first flow is dissipated in the second flow. But it will take 1.5 time of this one. It takes a large time, and it uses the same pressure releasing factor, but it is another way of algorithm. Okay. Simply, it is more, it's not meaning simple, huh? It is more for more turbulent steady state. So if this one simple but steady state, but it is way turbulent, so use simply. It use pressure reducing factor from 0.7 or less. It take twice the time of this one. Okay, and Bembly, it is same like Viso, but don't take it unless you find instability. So when it is not stable, Viso is not working with the transient, go to Bembly. As this method is simple plus Viso. This method is a combination between this one and this one. Okay. Now we are going to discuss about the diffusion and the scalar. From Einstein, it is a sign, it's not our famous Einstein, it's another one. It is the member Sherman guy or something. Relation is that the diffusion is equal to movability multiplied by Boltzmann constant multiplied by the temperature in Kelvin equal diffusion. Okay, uh, this is a constant. This is in Kelvin. So what is U? U movability. It is a ratio of terminal velocity to force applied. Okay, and for example, U for smoke is equal to 6 by eta. It's not eta as efficiency, but write it eta multiplied by K. It's not KB. K small k over 1 minus 1 as so it's not eta mu. So mu is a viscosity, for example, for the fluid. K is a particle radius of the smoke, which is approximately 0.1 to 1, and multiply, you will get. By the way, you can understand the diffusion for the smoke. Put all the numbers, it is from 1 to 2 multiplied by 10 to power negative 10 meter square per second. From the diffusion, we need to identify always the diffusivity. Diffusivity is the diffusion divided by density. We know density of smoke approximately is 0.5. So diffusivity, it is 1 multiplied 10. Some software use the diffusion directly. Some software using the diffusivity. You can use in the answers a certain number, or you can put it as an expression, a number divided by a density. You can use it like this. You can use it is based on the computing power, but I am advising you for smoke, don't make it too much complicated. It is the longest computing power you're going to face. It and the cooling towers. Okay, so it will not affect because the movement of the smoke, it is mainly not due to diffusivity. You are not simulating FM200. If you're simulating F200, no, but it is a function of force as always changing. But put it as a constant, and because the movement is due to the thermal movement, what we discussed here. So the smoke is moving due to thermal, high temperature, and above is low temperature. So because heat from the fire, so the smoke go up. It's not because of diffusion. It's not like FM200 or perfume. Okay. Okay. Case for water spray, we know, for example, a definition of water spray, this diameter, the droplet or the radius is like this. So we can define the diffusivity based on this above. You will put the new diameter, viscosity of the water, etc. Blah 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 blah. You will get the diffusivity, the diffusion. From the diffusion, you can write diffusivity. So if you have a water cooling tower and you're simulating the cooling tower, you start to put injection as a scalar with a defined function, and you can put it this number. Okay. Sometimes you don't have droplets, or like this, you have gas in gas, which is you don't know. So what to do? There is curves for diffusivity, for diffusion, and the temperature when this gas in the air going to be case, and it is available online, by the way. If you have a vapor, you have CO2, you have CO, you will check what is the temperature, you'll check the diffusivity. You can even write it in the answers, that is, it is a subject of the temperature if you want. If there is a big variant in temperature, for example, if you have, if it is just a room 24, a certain number, so you will get a certain number, you can put it. Okay. Okay. So this is the scalar and the diffusion, which is you can use it. Light visibility, which is the last before the last, light visibility, and a series of sorry, light visibility, then and the species and reaction. Light visibility, I will discuss it later.